we continue our study on planar kinematics of a rigid body. For general plane motion, we know we have three methods. The first method is absolute motion analysis, and this can be used for determining both velocity and acceleration. We studied this method in week 1. Week 2, we studied relative motion analysis, and this method can also be used for both velocity and acceleration analysis. In last week, we used this method to study the analysis on velocity. In next week, we will use this method to do analysis on acceleration. The third method is instantaneous center of zero velocity. This method can only be used for determining velocity. Of course, when we do acceleration analysis, sometimes we have to involve velocity analysis. We still can use IC method, but that's only for velocity analysis. For a certain problem, 2 or 3 methods can be used, but they have various difficulties. Basically, as a direct method, absolute motion analysis can be used for analyzing a simple problem of general plane motion. Relative motion analysis involves vector calculation. It can be used for any problems, but comparing to instantaneous center of zero velocity, you will see instantaneous center of zero velocity, this method, in most cases, can be much easier than relative motion analysis. We will study how to determine the location of instantaneous center of zero velocity of a rigid body undergoing general plane motion. And we will learn how to use this method to do velocity analysis. Firstly, let me introduce the basic idea of IC method. Here in this slide, you can see this equation, and we use this equation to do relative motion analysis of velocity. In this equation here, there are 2 points, A and B. Normally, we call point A at the right hand of this equation. We call this point as base point. In week 2, when we use this equation to solve some problem, we have already known how to select these 2 points. But here you can see, for this base point A, is it possible for us to select a point A, and this point A, its velocity is 0. If this is possible, then this equation will be simplified to the equation like this. In this equation here, because the velocity at point A is 0, so now we only have Vb and omega You probably already found this equation is as similar as the equation we introduced in rotation about a fixed axis through point. This means if we can select a point A, and at this point A, the velocity is 0, then A will be IC point, and at this instant when A is the IC point, the body undergoes rotation about axis through point A. This IC point can be on the rigid body undergoing general plane motion, but it's not necessary, and sometimes you will find this IC point is out of the rigid body. Let's have a look two cases. In the first case here, you can see a wheel. This wheel is rolling on the ground. We already know for a wheel or a cylinder, they are rolling on the ground because the velocity of the ground is 0. So the contact point between this wheel and the ground, this contact point on the rigid body, for example this wheel, this point must be the IC point. Why? Because we assume no slipping. At this contact point on the wheel, if its velocity is not 0, then there will be a difference between the velocity of the contact point on this wheel and the point on the ground. So slipping will occur. But here we assume no slipping. So the velocity of this contact point on the wheel must be 0. The body is not necessary to have a circular cross section. Let me show you a video. In this video here, you can see this car is rolling. And this is the general plane motion. If we assume no slipping occurs between this car and the ground, then at any instant the contact point between this car and the ground, the velocity at this contact point must be 0. And the contact point on this car should be the IC point. In this second case, you can see a board slides down the wall, and we already know this kind of motion. When this board slides down, it's a general plane motion. At point B, the velocity Vb is vertical downward. At point A, the velocity Va is horizontal to left side. And in this case, the IC point is here. and this point is not on the rigid body. Now, the question is why this IC point should be here, and how to determine its location. Boundary conditions in different problems can be different. So, how can we determine the location of the IC point? It sounds difficult, but actually there are only 3 cases. In the first cases, you can see here there is a rigid body, and in this case here, we know the velocity of point A on this rigid body, and we know the angular velocity of this rigid body. In this case, how to determine the location of IC. We already know the IC point is the rotation axis through point at this instant. More accurately, IC point is the instantaneous axis through point. So if we connect the point A and the IC point, this line must be perpendicular to the direction of VA. But what should be the distance between point A and the IC point? This distance can be calculated using VA divided by omega. Now, we still don't know where the IC is. Should the IC point be on the right side of VA or the left side of VA? We have to look at the direction of angular velocity. In this case here, this angular velocity is clockwise. Then that means the location of the IC point must be on the right side of VA. The second case, in this case here, we have one rigid body and it's undergoing general plane motion. We know the velocity at point A and the velocity at point B. Again, because the IC point is the instantaneous axis through point, so we know if we draw a line connecting point A and IC, this line must be perpendicular to point A. Next, if we draw a line connecting point B and the IC point, this line must be perpendicular to the direction of VB. Okay, now these 2 points, these 2 lines give us an intersection point, and this intersection point will be the IC point. In the third case, we have a rigid body undergoing general plane motion like this, or or this one. We know two parallel velocities. So for example, in this situation here, we know point A and point B. At these 2 points, the velocities are parallel to each other, but they have opposite directions. In another situation, we have point A and point B. They are parallel to each other, and they have same direction. As same as before, if we draw a line connecting the IC point and point A or point B, this line must be perpendicular to the direction of velocity Va or Vb. So that's the line. IC must be on this line. Then, if we draw another line connecting the end point of Va and the end point of Vb, in this situation, the end point of Va and the end point of Vb, you can see these two lines have an intersection point here or here, and this intersection point will be the IC point. The special case here is if we have Va is equal to Vb. Be careful here because velocity is a vector. Va is equal to Vb means their magnitudes are same, their directions are same. In this special case, where the IC will be. Okay, look at this. It's a rigid body. We assume it's undergoing general plane motion at point A and point B at this instant. Their velocities are exactly same magnitude, same direction. Okay, for determining the location of IC, we have one line perpendicular to VA, another line perpendicular to VB, and you will see these two lines are parallel to each other. So this means no intersection point can be found between these two lines. What does this mean? This means at this instant, no IC point, and this rigid body at this instant is actually undergoing a translation. This time period in this animation is exaggerated, and actually this is a very, very short time period. At this instant, the rigid body is undergoing translation. Now, the essence of general plane motion. We already know general plane motion is a combination of rotation and translation in a period of time. A period of time consists of indefinite instant. At a certain instant, the rigid body may undergo either rotation or translation. If it undergoes a rotation, then the IC point will be the instantaneous axis through point. If it's a translation, then the IC point does not exist. The location of the IC point always changes when a rigid body undergoes general plane motion in a time period. A path can be observed when tracing the locations of the IC point. At some instance, because the rigid body may undergo translation, at this instance, for example, these three instances, no IC point exists. Okay, look at this animation. This rigid body is undergoing general plane motion in a time period. If we trace the location of the IC point, you can see from C to C prime to C double prime. And this is the curve, and this is the path of the IC point. If we can locate the IC point, for example, for this rigid body undergoing general plane motion, if we know the IC point is here, then for any other points on this rigid body, A, B, C, we can easily determine their velocities. So for example, for point A, we connect IC and point A, and the direction of VA must be perpendicular to this line. For B or C, same. And also, if we know the direction of angular velocity of this rigid body, for example here, it's counterclockwise, then we can easily find the direction of VA, VB, and VC. One advantage of using IC method is we don't need vector calculation. We only need scalar calculation. But you will ask, velocity is a vector. If we only use scalar calculation, how to determine its direction? It's not a problem. Actually, as you can see here, if you know IC, you know the direction of angular velocity, you will know the correct direction of VA, VB, or VC. Or if you know the IC point and you know the direction of VA, then you can easily determine the direction of the angular velocity omega. Let me show you another video. Okay, and in this case here, a disk or cylinder is rolling on the ground without slipping, so the contact point C is always the IC point. Then, if you know C is IC point, to determine a point, for example, point B, the velocity at point B, then you just connecting B and C, then the direction of VB can be easily determined. It must be perpendicular to the line connecting C and B. And in this case, because omega is clockwise, so VB to that direction. Now, some examples. For these examples, I'm not going to give detailed calculation, but I will do analysis and I will draw all necessary diagrams. Example 1. In this example 1, you can see two mechanisms. And in this one here, there is the crank AB, and this one is undergoing rotation about a fixed axis 0.8. A piston C is undergoing rectilinear translation. Link BC is undergoing general plane motion. And we will do velocity analysis on BC. Okay, we will need to draw the kinematics diagram. For this mechanism, we can draw two diagrams, one for crank AB and another one for link BC. We only look at link BC because it's undergoing general plane motion. We can't find enough information to determine the velocities of any points on this rigid body. But B and C, these 2 points, are pin connection points. So for point C, because this is the pin connection point between BC and piston C. For piston C, it's undergoing translation, rectilinear translation. So its velocity must be horizontal. So we can have a line going through point C, perpendicular to the velocity of point C is horizontal. At this moment, it doesn't matter is to left side or right side. Okay, one line. For point B, look at the crank AB. Because AB is undergoing rotation about a fixed axis 0.8. And we already know AB, its angular velocity is clockwise. Sorry, here I missed the angular velocity omega AB. Omega AB should be clockwise. So that means VB, its direction must be perpendicular to AB, and VB must be downward instead of upward, because omega AB is clockwise. Then what we can do is copy everything from point B on rigid body AB from here to here. Then we know the direction of VB on rigid body BC. Now we can have another line going through point B and perpendicular to VB. Okay, this line and this line, these two lines will have an intersection point, and this point will be the IC point. Now, another mechanism. In this one here, we have three links. One is CD, and this one is undergoing rotation about a fixed axis through point D. We have another link AB undergoing rotation about a fixed axis through point A. Link BC is undergoing general plane motion. And here we already know the direction of omega DC. For this mechanism, we need to draw kinematics diagrams for each link. For DC, for AB, and for CB. If you only look at CB, you don't know anything. But C and B, these two are the pin connection point, so we will look at these 2 points. C is pin connection point between DC and CB. For DC, it's undergoing rotation about a fixed axis through point D, and its angular velocity omega DC is clockwise. So that means its velocity Vc must be vertical downward. Then we can copy everything from here to here. For point B, it's a pin connection point between CB and AB, because AB is undergoing rotation about point A. So we know at point B, the direction of VB must be perpendicular to AB. So this means VB must be vertical. By observation, because VC is downward, so we know VB should be downward. And we can copy everything from here to here. Now we got VC, we got VB. And you can see both VC and VB, they are vertical. So we have one line going through point C and perpendicular to VC. Another line going through point B, perpendicular to VB. These two lines must be parallel to each other, so they have no intersection point. So this means at this instant, no IC can be located for link BC. And at this instant, link BC is undergoing translation. But just at this instant, immediately before this instant, or immediately after this instant, it will not be translation. Now, the second example. In this example here, you can see a big gear, a small gear, and a gear rack. The big gear and its small gear, they are actually connecting to each other. So no relative motion between these two gears. And this small gear engages with the gear rack. And normally we think no slipping between a gear and a gear rack or two engaged gears. And here we already know the velocity at point O, it's 6 meters per second. And this velocity must be horizontal. Why? Because the distance from this center point O to the gear rack is always the same. So this means for point O, its moving path is a straight line. So its velocity must be horizontal. Okay, we draw a kinematics diagram. And here, because we already know no slipping between this small gear and the gear rack, and this is a rolling motion, so the contact point here between the small gear and the gear rack, this point must be the IC point. Okay, the target here is the velocity at point A. Because we know IC is here, so we connect point A and IC point, we have one line, and VA must be perpendicular to this line connecting A and IC. But should this VA upward or downward? It depends on the direction of the angular acceleration of this rigid body. What should be the direction of the angular velocity of this rigid body? We look at VO. VO is horizontal. If we connect point A and IC, this line must be perpendicular to VO. VO to right side. IC is here. That means the angular velocity must be clockwise. If the angular velocity must be clockwise, then in this one here, point A, VA must be upward. Now, next example. And here, there is a cylinder rolls without slipping between the two moving plates E and D. No slipping between this cylinder and the plate E. No slipping between the cylinder and the plate D. We already know the velocity of this plate E and the velocity of plate D. So the target here is the angular velocity of this cylinder and the velocity of its circle center C. Okay, here, no slipping at point A, no slipping at point B. My question is, are these 2 points IC points? The answer is no. Why? This cylinder is undergoing general plane motion. No slipping here, no slipping here. but plate E has the velocity 0.25. Plate D has the velocity 0.4 meter per second. So this means no slipping at this point A and point B, but at this point A and point B, the velocities are not zero, so they are not IC point. But where should be the IC point? Look at this kinematics diagram, and this is the cylinder. At point A, no slipping, so at point A, the velocity Va must be equal to the velocity of plate E, 0.25 meter per second. At point B, another contact point, Vb must be equal to the velocity of plate D, so it should be 0.4 meter per second. So you can easily find this is the third case when we learned how to determine the location of IC. What we can do is connecting point A and point B. Connect the end point VA and VB. These two lines have an intersection point here, and this point is IC point. Okay, so it's easy to determine the IC point using this diagram. And its distance, its location, its distance between IC and B, we can assume is X. And we can use calculation to determine its X. And here, I just let you know how to draw this diagram. A question here is, if plate D and plate E, they have same velocities, what will happen? If plate E and plate D, they have same velocity, sorry, what I mean is their magnitude, not direction, then VA and VB magnitude must be same, but the directions are different. So in this case, you will find IC point will be the circle center point C. Now, the question is, if the IC point coincides with the circle center point C, what motion does this cylinder undergo? What will be the motion? You will find it will not be a general plane motion. It becomes a rotation about this circle center C at any instance. And this will be a rotation about a fixed axis through point C, because C is always the IC point in this case. Of course, this axis is not a physically fixed axis, but just a virtual fixed axis. Okay, this problem is very typical links problem. And here you can see link AB, link BC, and link CD. AB is undergoing rotation about point A. CD is undergoing rotation about point D, its angular velocity, direction counterclockwise. BC is the link undergoing general plane motion. Okay, we can have kinematics diagram for these three bodies each. For CD, it's undergoing rotation about a fixed axis through point D. So we know because at this moment CD is vertical, so VC must be horizontal because omega CD is counterclockwise, so VC to left side. For AB, we know it's undergoing rotation about point A. So VB, its direction, must be perpendicular to AB. Now look at the link BC undergoing general plane motion. We can copy everything from point C on CD to point C on link BC. We can copy everything from point B on AB to point B on BC. Then we can draw one line connecting going through point C perpendicular to VC. Another line perpendicular to VB and going through point B. So these two lines will give us an IC point is here. This is the intersection point. Now for point E. For point E, we connect IC and point E. Velocity at point E, VE, must be perpendicular to this line connecting E and IC. Because VC, its direction can be very short from link CD. So this means for link BC, its angular velocity must be clockwise. Then you will see the direction of VE or VB, they must be upward. That's the diagram, kinematics diagram for solving this problem. The calculations in IC method are always a scalar calculation. So it should be easy to deal with.